Welcome to this complete MySQL course. If you've never worked with a database before, if you're just learning about it, or if you used to work with it and just need to be reminded about how it was that it worked, this course will take you from the simplest beginner steps and into advanced MySQL in small increments so that everyone can follow along. So even if you never touched a database in your life before, you'll be able to understand complex databases by the end of this video. My name is Henrik, and I'm a software engineer, full-stack developer, consultant, and university teacher. So I work with these technologies every single day, and I've taught these concepts to thousands of people already. SQL is shorthand for Structured Query Language. It's a domain-specific language built for interacting with data in a database management system, or DBMS. There are many database management systems such as MySQL, MariaDB, Postgres, Microsoft SQL Server, SQLite, Oracle DB, and the list goes on. All of these are relational database systems which you can interact with using SQL. However, there are slight details that vary between these systems, so while this course would generally teach you how to use all of these, you might run into a couple of syntax errors that you need to look up if you're not using MySQL or MariaDB. MySQL is a DBMS developed by a team where one of their daughters was named My, and that's the reason for that name, MySQL, just in case you were wondering. MySQL used to be open source, free to use and actively developed, but after Oracle bought it, part of the original development team felt that development had stagnated and utilized the open source nature of MySQL to make a fork of it called MariaDB. Fork is Git language and means a copy, and since then they've added features while making sure to maintain full compatibility with MySQL. That means that in most applications that use these systems, MariaDB is actually preferred over MySQL. But if you need to look up the syntax for something on Google or Stack Overflow, you need to look for the MySQL syntax, not MariaDB, even if you're using MariaDB. You might have noticed that I'm talking about database management systems. That's what these different variants are called. That's because a single DBMS can actually contain multiple databases. So when you install MariaDB and create a database in it, that's what we call a database. And these names help us differentiate between the installed system and each of the databases inside it. In order to work with SQL, you need to install a database management system. It makes no difference if you install MySQL or MariaDB, but in this video, I'm using MariaDB. In some cases, the installation process is simple and straightforward, but in other cases, it can cause a bit of trouble. And if you run into such trouble, I have a video that walks through the installation of MariaDB on both Mac and Windows, and there are links to them both in the description below. So now that everything is set up and ready, let's talk about how databases work. Database users and system users. We already talked about how databases are things that live inside a database management system. But there are a couple of other things we need to get out of the way. When you installed your database, you created a user, most likely named root. And you can create multiple users for your database with different access rights. These are system users though. Usernames and passwords that you and your applications can use to access the system. When you build a web application at some point or install a system like WordPress where users log in with a username and a password, that username and password has nothing to do with these users. Those users will be stored in a table in the database and handled by an application that has access through one of these DBMS user accounts. But WordPress itself, or whatever application you want to install, will need one of the system user accounts, for instance root, but it could be something different. So tools. There are a couple of different ways that we can communicate with our database management system. We can use the command line interface. If you're on Mac or Linux, you can open up the terminal, and if you're on Windows, you can open up the command prompt, and then just write mysql.start, and after entering your username and password, you can start typing in SQL, one command at a time. You can also install a desktop application. If you installed MariaDB on Windows, then it already came with HeidiDB. Another alternative would be DBeaver, which is completely free in the Community Edition and works with all the major database management systems, including MySQL and MariaDB. If you're using one of these tools, you're looking for a place that says Query to insert your code. And you need to be aware that some things don't work right after you run your code because you need to click the commit button. And some things are not visible right after you create them because you need to click refresh. If you're going to be working with PHP and already have PHP installed, then you can either install PHPMyAdmin or Download the simple PHP script from my GitHub that just lets you write SQL code to your database via a browser without installing anything else. The benefit of that is that if you want to work on a web hotel or any other place that has PHP installed, you can simply copy this code and it'll work without any installation. You do need to remove it immediately after use though, and avoid getting it into any production site, as it obviously is a major security issue to have a script that lets you type anything you want directly into a database. There is a link in the description, and all you need to do when you run it is to provide the right database name, username, password, and everything should work. Let's get into the syntax and creating databases. SQL syntax is made to feel a lot like a spoken language, but even so, it's built with a number of keywords that are specific for the programming language, SQL. In MySQL, conventions suggest that you write SQL keywords in uppercase letters and the name of your own entities in lowercase letters. So when we create our first database called webshop, I'm going to write create database in uppercase letters and webshop in lowercase letters. And you can see that throughout this video, whenever I'm using uppercase letters, that means that I'm using keywords from MySQL. And when I'm using lowercase, that's because I'm working with the part that I've built into it myself over the course of this video. But with all that being said, this is a convention. MySQL itself doesn't really care. If you write everything in small letters or capital letters, go for it. It's fine. It works. This is just the convention that makes it way easier for other people to read it and figure out what it is that you're trying to do. If you want to see all the databases in your DBMS, you can write show databases. When you do this, you'll see that there are actually already a couple of databases in your system, and some of these hold metadata about your current setup. If you created the database or connected to your system, you need to write use webshop in order for your following commands to work on that specific database. If you're using the PHP script from my GitHub, then you need to jump into it and change the database name to webshop after you created it. If you need to delete the whole database later on, you can do that by writing drop webshop. So let's create some tables. Now that we have a database, we need a table that we can store our structured data in. This is going to be quite a mouthful, so bear with me. I promise it's going to make sense in a couple of minutes. See, the thing is, you can't just create a table without any columns in it. So we might as well create a proper table and then just start breaking it down, explaining what's going on. You ready? Okay. So one thing that we almost always need to work with is users. So let's go right ahead and create a user table. So I have some code here. Create table user. And then I have a parenthesis that contains the rest of the code. And after that parenthesis ends, I have a semicolon. So inside that parenthesis, it says user ID, serial, primary key. Email, varchar 126, unique. Email validated, boolean, default, false. Password, varchar 126, not null. Created at, timestamp, default, now. Notice how I'm listing multiple columns inside the parentheses separated by commas. Also notice that I'm creating an ID as the first column in my table. This is a way to make sure that all my users can be identified with a number so I can recognize them as the same user even if they change their username or their email address later on. This is generally best practice in most tables, with the exception of strictly relational tables, which we'll get to later with the shopping cart. There's a number of different data types in MySQL. You can see the email is a varchar, email validated is a boolean, and created at is a timestamp. So let's take a look at these data types. Integer numbers can be saved as tiny int, or big int, depending on how large numbers you want in it. If you know that you're only ever going to work with positive numbers, such as when you have an ID, you can add the keyword unsigned after you declare it. That way, the integer will have twice as many positive values to work with because it doesn't have to deal with any negative numbers. Boolean is made for true or false values, but in MySQL, booleans are really tiny ints that translate false to 0 and true to 1. If you need decimal numbers, you can use the data type decimal followed by two numbers in a parenthesis. The first number is the number of digits in the whole number before the decimal point, and the second number is the number of decimal points you want to have after. For text, you can use char or varchar. A char needs to know exactly how many characters you need, A varchar needs to know the maximum number of characters that are going to be in that column. That's probably the most used data type, by the way. If you work with long form text and you need to allow more than, say, 500 characters, you should generally use text instead. And once again, you have tiny text, text, medium text, and long text. If you have files that are converted into text for storage, you can use the data type blob. Text and blob can be set with different sizes depending on how much data you need in it, with medium blob and large blob. If you want to know more about converting files to text using base64 so that you can save them in your database, I have a video for that linked right here. But you can, of course, always store your files on disk and just use your database to store the URL for the files. Time. So you have time, date, year, then you have date time and timestamp. Dates can only represent date, times can only represent a point in time, year can only represent a year. But date time and timestamp can represent both time and date. The difference between them is that date time saves the date and time with the time zone, whereas timestamp uses the time as specified by the time zone set in the DBMS. In most cases, you should use that and then adjust time to the right time zone in other parts of your application. Sometimes you might need a specific data type like a string, but where you always want to use the exact same word every single time. So maybe you want to have some categories. You can do that by using the enum data type. You can also use the set data type, which does the same thing, but allows you to have a list of selected values instead of just that single value selected in every field. If we go back to creating our table, we can now see that all of the columns have a name followed by a data type. After that data type, you see things like primary key, unique, not null, default. These are called constraints. They set up further requirements for the data that you put into the table. Let's go through the most common ones. Not null. That means that you have to put some data into this column when you add data. Later, when we add data to our tables, we can select which columns we want to insert data into and then just ignore the rest. But if we try to ignore a column with the not null constraint, an error will be generated and the data will not be inserted. Unique will require each entry into the table to have a new value. For instance, if you have users in your system who log in with their email addresses, it's pretty important that you cannot create two users with the same email address, so we add the unique constraint to them to avoid that. Default is a bit different in that it actually sets a predefined default value in the database if nothing was given. This can be used with all data types as long as the default value you gave it has the correct data format. Some data types have functions that you can use with this, such as the timestamp, where you can set default current timestamp. That means that whenever you insert new data into the table, the new row will get a timestamp that matches the time when it was inserted. If you need to automatically update a timestamp whenever another data point in the same row is edited, you can do that by saying on update set current timestamp. But we're getting ahead of ourselves now. Auto increment can be set on an integer to make it count. That way, the next entry will always get the next number in a sequence. This would result in something like what you know from Excel, where each row has a number. If you delete a row later on, auto increment ignores that and just keeps counting from where it came from. That's because otherwise, a new user might get the ID of an old user, and if there's a bug in your system, then they might get access to a bunch of data that they shouldn't have. So it's better to just leave used IDs alone and never use them again. So this gets us to keys. Most tables need a primary key. A primary key is something that uniquely identifies a row. Typically, they're of the type int or big int. But a primary key is actually an index. This means that the database sorts data by it in order to find it faster later on. You can add an index to any column if you want the database to be able to find data faster in it, but this is at the expense of writing the data slower, since it has to be sorted every time you insert something new. The problem with slow write speeds is that the table is actually locked by the DBMS while you write data to it. That's not the case for reading, but on the other hand, you will be making a lot more reads than writes, so maybe it is worth the trade-off. At least consider which columns you'll be using to find your data later on, and make sure to add indexes to them. In our user table, we'll most likely be searching for users by their email, so it would make a lot of sense to turn that into an index. So if we would write show indexes from user, we will see that the email column already is an index. That's because we added the unique constraint to it when we created the table. We can delete that index by saying drop index email on user. And we can create it again using create index email on user parenthesis email. So that means the column email in the table user. If we show the indexes again, we can see that it's back, but it's no longer unique. So we would actually allow multiple users to have the same email address now. That's not what we want here. So let's drop the index one more time and create it as unique. Create unique index email on the email column in the user table. A unique index can also be used to set a unique constraint across columns. For instance, create unique index email on user and then email, email validated. That will create an index where you can still have the same email address multiple times, but you couldn't have two of the same email address that were both validated or not validated. Something would have to be unique in one of the columns, and you can of course list more columns inside this parenthesis. Primary keys and foreign keys. So since the primary key in a table is the unique identifier of a row, we can also use it to bind data together. We're creating a user table right now, but let's say we wanted to create a web shop. Then a user might need to have several addresses. We would then create the following table. Create table address. Once again, we have the parenthesis that ends with a semicolon, and inside that we put all of our columns. Now, let's see if it makes a bit more sense this time. Address ID. Yeah, serial, primary key. User ID, big int unsigned. Foreign key, user ID, references the user ID column of the user table. Address, varchar 126, zip, varchar 14, zip, varchar 62, and country, char 2. So the line foreign key user ID references the user ID column in the user table means that the user ID column now expects a value from the user ID column in the user table. In other words, we're binding the address to the user by binding the rows with the keys. So the foreign key of one table is the primary key of another. Notice how binding the foreign key is its own line. We could easily leave it out and everything would still work fine. We could still reference primary keys from it, but we might end up using an ID that doesn't exist. The problem with binding keys is that it becomes difficult to delete data. So if you create this table, add some addresses to a user, you'll no longer be able to delete that user or drop the user table because there's other data in the database that relies on it. And that's great. That's exactly what we want in a production system. But if we're just playing around, learning MySQL, or designing the baseline for a system, we might want to leave out the foreign keys and then add them at a later point. We can remove the foreign key constraint with the query alter table address drop foreign key address underscore ibfk underscore 1. And then we can create it again later using alter table address add foreign key user ID column in the address table references user ID column in the user table. So how did we know that the foreign key was named address underscore ibfk underscore 1? Well, it's the name of the table, an underscore, then ibfk, an underscore, and 1 because it's the first foreign key in that table. If we're in doubt, then we could look in another database. The information schema holds metadata about other databases, and we can run the following query. Select table name, constraint type, constraint name from information schema.table constraints, where table underscore name equals address or table name equals user. Then we can see the names of our constraints in case we need to drop them. If you already deleted the constraint and created it again, it's most likely just called address now. If we know we might be dropping a constraint later on, we can just set the name ourselves when we create the constraint. Alter table address, add constraint fk address user ID, foreign key, the user ID column in the address table references the user ID column in the user table. So now we know that the constraint is called fk underscore address underscore user underscore ID because we said so. So the last thing in that create table statement earlier that we haven't addressed yet is the word serial. When we create a primary key, we would normally want it to be an unsigned big integer that auto increments, it should not be null, and it should be unique. But that's quite a mouthful, especially for something that we'll be writing over and over again. Remember that we'll need this for most of our tables. So the keyword serial is simply a shortcut for that. Serial is the short way to write big int, unsigned, not null, auto increment, unique. That's what serial means. It's a direct translation. If you wanted to write out the longer syntax, that's perfectly valid as well. Serial is just a short way to write that. So let's take a look at creating that user table one more time. Create table user creates the table and gives it the name user. User ID, serial, primary key, makes a properly named ID. Serial turns it into a unsigned big int, and primary key lets us identify the data later on. Email, varchar 126, unique not null, allows us to insert up to 126 characters as an email address, but doesn't allow us to use the same email address twice. Email validated boolean, default false, really creates a tiny int where 0 will mean false and every other value will mean true. Password, varchar 126, not null. That doesn't have anything we haven't seen before. Created at, timestamp, default now. This makes sure that the database management system automatically fills in the date and time when a user is created if we don't provide a timestamp ourselves. Let's create a couple more tables so we have something to work with in the next section. We'll turn this into a web shop, so let's create some tables that support that and look at a couple of the things we haven't tried out yet. Create table item, where we have an item ID, we have a title, we have a price where we're using the decimal we talked about earlier, with 8 digits before the decimals and 2 decimals. We have a description where we actually use text because we expect a longer format of text. Image is going to be a long blob, so we can actually convert a file into some text and put it into that column. We won't be doing that here, but it is something you can do. I have a separate video on doing that if you're interested. Category, enum, has a parenthesis after it where it says food, garden, animals, and then not null. So you have to pick a category when you insert an item, and it has to be one of these 3. In this table, we're using decimal to specify a price with exactly 2 decimal points and an enum that forces us to choose if each item belongs to food, garden, or animals. Then let's create a shopping cart, where each user can have their own shopping cart. This table will be a relational table, so we won't be giving it a primary key. Its only function is going to be to bind 2 other tables together. Create table shopping cart, and inside the parentheses, we have a user ID and we have an item ID. Both of them are foreign keys to the tables that they'll be referencing. And then we have a last column that says item amount. Now, the reason that we build a relational table like this is that a user cannot just point directly to an item, as that would restrict each user to only having a single item. We also cannot relate an item directly to a user, as that would constrain each item to only belong to one user. In other words, this is a many-to-many connection. Had it been a one-to-many connection, we could simply have used the existing tables like we did with the addresses. There, we could have multiple addresses for a single user because the address just references the user. Had we done it the other way around, had we put the address ID onto the user table, then we could have had multiple users on the same address. So to make this first section complete, let's remove, add, and rename a column. Alter table, shopping cart, drop column, item amount. Now that column is gone from the table. Alter table, shopping cart, add column, amount, int 11. That gives us an extra column in the shopping cart where we can select how many of each item that we want. But let's rename it from amount to item amount to make it perfectly clear that this is one user wanting several items and not the other way around. Alter table, shopping cart, rename column, amount to item amount. Normally, when we build relational databases between 2 other tables, we name it by combining the names of those tables with an underscore in between. So this table should have been called user item. But to avoid confusion in this introductory course, I've chosen a more semantic name. In programming, and especially in data, we talk about CRUD. Create, read, update, delete. That's the 4 general things that you'll want to be doing with data. In SQL, we differentiate between working with the tables themselves and the data inside those tables. When we work with tables, we use create to create, we use alter to update, and then we use drop to delete columns or tables or databases. You can show tables to read what tables exist, and you can use describe user to read the structure of the user table. And that should be enough to get us started. So let's jump into the next section of the course, working with some data. So let's start things off by creating a user. Let me repeat that you should never have passwords as clear text in your database. But since that's something you would normally handle in your backend system, we don't have a lot of real choice right now. So insert into user, and then we have a parenthesis that says email password without any quotation marks. Then it says values, and we have another parenthesis where it says jack@skillsession.net and mom. So let's dissect that. First of all, I'm not doing anything to insert data into the user ID since it's incrementing the ID automatically. I'm not setting the email validated column either, since an email address would never be validated upon creation and the default value is set to be false or 0. The created at timestamp is also set automatically. So even though we only filled out 2 of the 5 fields, all 5 fields have meaningful and important data. We can use the same query to insert multiple rows at once. So let's create 3 users more. Insert into user, parenthesis, email and password, and values. Joe@skillsession.net with the password mom, Jill@example.com with the password dad, and Jane@test.org with the password sunshine. Notice how the only thing that's repeated is the last parenthesis. As long as each parenthesis follows the pattern set in the first one, we can repeat as many parentheses as we want to. And if we write select star from user, we can see that our users have the IDs 1 to 5. So let's insert some items that we can shop for. We can write describe item to see how the table looks in case we forgot. Let's insert some items then. Insert into item. Title, price, and category with the following values. Beans at $19.99 in the food category. Lawnmower at 1,000 in the garden category. And ostrich at 716.61 in the animals category. In order to insert some addresses, we need to know some user IDs. So let's write select star from user. Now my users have the IDs 1 to 5. And I just want to add 2 addresses to one user, 1 address to another user, and then an address that doesn't belong to any user. So insert into address, user ID, city, country, with the following values. User 1, Duck City, in the country UK. Remember, the country had to be exactly 2 letters. User ID 1, again, this time in Atlantis City, country DA. User ID 2 this time. City is going to be Gotham and the country is going to be ME. Whatever that stands for. It's 2 letters. And then the user ID null. So I'm not choosing a user for this one. I'm leaving it empty. In the city Gotham. And once again, the country is going to be ME. So the first value is just a number, the user ID. That's how we bind the addresses to our users. In the last line, we write null instead of a number, and that way we're ignoring the binding and simply adding an address without saying whose it is. Normally, we would add more detail to an address, but when the field don't have the not null constraint, this is perfectly valid. Lastly, let's add some items to the shopping cart. The items we created have the item IDs 1, 2, and 3. So let's say that user 1 needs a couple of ostriches and a lawnmower, and user 2 needs a lot of beans. So insert into shopping cart, user ID, and item amount with the following values. User ID 1 gets an item ID 3, and they get 2 of those. User ID 1 gets an item ID 2, and they only get 1 of those. And then user ID 2 gets an item ID 1, but they get an item amount of 100. Now, this last data probably looks like gibberish for now, but it will make a lot of sense when we get into the joins later in the course, and I do have timestamps enabled if you want to jump over and look to that before you jump back here. So now that we have some data, we can read it by saying select star from user. Select means that you want some data, star means that you want everything, that this could be replaced by a list of columns, so you could write email, password, I could also alter the data by saying update user set password equal to sunshine. This uses the keyword update to state that an existing value needs to be altered. The table name is followed by the keyword set and the name of the column where the new value should be inserted. This would be an uncommon command though, since it would update all the passwords for all of the users in the table, and everyone's password would become sunshine. Likewise, the user can be deleted by writing delete from user. Once again, the keyword delete is used to state the intention of the request, and the keyword from precedes the table name. And like the update statement, this one would be rather uncommon, as it would, again, delete all of the users. So let's recap CRUD before we move on. Create, read, update, and delete. When it comes to data, we use the keyword insert to create data, select to read data, update to update data, and delete to delete data. So now we can build and alter our tables. We can build and alter our data. Let's search for it. Create, read, update, and delete makes a lot more sense if we can define the specific data we want to work with. In SQL, search is done with the where keyword. So if we want to find the users whose passwords are mom, we can create select star from user where password equals mom. Once again, values are passed in single quotes. You can get the opposite result by adding an exclamation point before the equals sign. So that would be select star from user where password isn't mom. If it was numbers, we could say something like select star from item where price is over 300. And notice how numbers don't need quotation marks around them. Now let's get back to our password example. If we don't know the exact content we're looking for, we can just search for something that looks like something else using the like keyword. That allows us to use wildcards like the underscore that accepts any character in its place. So we could say select star from user where password like m_m. That's going to find the users who have mom as a password, but it would also find them if they had the password nam or something similar. If we don't know the length of the text and just want to search for something that we know exists within the string, we can use the percentage sign as a multi-character wildcard. Select star from where password like percentage sign, sh percentage sign. So each of these percentage signs can be replaced with any number of any characters, including none. And sometimes you just want the values that exist or don't exist, and for that you'll use is null and is not null. For instance, select star from user where password is not null. That would get us all the users who have a password, whereas is null would do the opposite. You can of course combine search terms and say something like select star from user where password like %ne and email_validated equals false. You could also use regular expressions or regex to achieve the same thing. And on an even more granular level, the great thing about regex is that it's universal and you can use it across programming languages like JavaScript, PHP, Java, Python, Node.js, whatever you want. And of course, here in MySQL. Let's find the users whose email addresses contain the letter A before they have an @ sign, and in between those two, they can have any number of random characters. So select star from user where email regexp a.star @. Now, if this regex looks a bit confusing, don't worry. I have a whole video on regex on the channel, and I'll leave a link in the description below. And I promise you, regex is worthwhile learning. If you want to do advanced text search in the larger text columns, you should use the match functionality. But in order to do that, you need to add a full text index to the columns that you want to do it on. So let's do that on the titles and descriptions of our items. Alter table item, add full text to title and description. Now we can search in full text indexes across these text fields using the match and against keywords. Select title description from item where match title description against ostrich. Now we don't have a lot of text in this database, so this might seem nonsensical, but if you had really long descriptions of your items, this would be exactly the right way to search for that. Now, sometimes you need to make a complex search and then get the opposite results. So instead of trying to negate all of the comparisons, you can simply find all of the things that you don't want and then ask for the rest. Select star from user where user ID not in and then a parenthesis. And in this parenthesis, we say select user ID from user where password equals mom. Now, that middle select query is going to return a list of user IDs where the password is mom. And we're asking in the outer SQL query for all of the users who have a user ID that's not in that list. So the result is going to be that we get all of the users out who don't have the password mom. In this case, it's rather simple, so we would probably not do it this way, but if you have a more complex query, this can easily become necessary. The last search topic that we're going to cover this time is if we want to get all the users who were created within the last hour, we could use the following syntax. Select star from user where created at is bigger than or equal to date sub and then a parenthesis. In that parenthesis, we say now interval 1 hour. You can replace the now function call with another function call or with a specific timestamp or with a function or even with a select statement like we saw just before. And we can select other intervals such as second, minute, hour, day, week, month, or year. For instance, we could say select star from user where created at bigger than or equal to date sub and then replace the now function call with select created at from user where user ID equals 11 and interval to 3 days. So this would give us all of the users who were created within the last 3 days before user 11 was created. Now that we can search and find all the things we need, let's look at how we present the results. We can select which column to order the search results by using the order by keywords. Select star from user, order by password. We can combine these in case we have multiple rows that have the same value in the sorting column. Select star from user, order by password, comma, email. In some databases, we might get thousands of results, or even when we do something like this, but we can limit the number of results we get by using the limit keyword, followed by a number. The limit needs to come after the search and the order, so it could look like this. Select star from user, order by, password, limit 2. This, of course, removes some results, but that's the point. Now we can look at the first 2 results, and when we're ready for the next 2, we set an offset to say how many results we want to skip. Select star from user, order by password, limit 2, offset 2. This is how you make pages with lots of results where you can go from page to page. That's called pagination. But how do you know exactly how many results there are so you can calculate exactly how many pages you need? Well, you can select a count of the results rather than the results themselves. Select count star from user where password equals mom. And this will show us how many users have that password. Likewise, if we had items in the store, we could find the average price with the following query. Select average and then price from the item. We could also use the sum to figure out what the total price is. Sometimes we just want a list of the different values. Maybe we want to see what categories were used in the items or what passwords were used for users. We can use group by to make sure we only get results where the column of a value is unique. So if we write select star from user, group by password, notice how we only get one user who has the password mom, even though there were actually 3 of them. Or we can write select password, comma, count star or count password from user, group by password, and see how many people have each of the existing passwords without knowing beforehand what those passwords are. So let's talk about joins. So far, we've only taken data out of a single table at a time, but when we look at an address and it has the user ID 1, to the human eye, that's gibberish. So let's just ask for that in the same query. Select address.star, user.star from address. Join user on address user ID equals user.user ID. This gives us the addresses that exist, but with the fields from the user table attached via the user ID fields. And actually, since we're using proper naming conventions and calling our IDs the table name underscore ID so that they have the same name in every table where we reference them, we can use an even simpler syntax now. Select address.star, user.star from address. Join user using user ID. So that only works because the column is named user ID in both tables that we're working with. And we actually don't even need to list the tables in the select query. I just wanted to make it visible how you select columns between tables now that we're joining them together. So you do that by saying the name of the table, then a dot, and the name of a column. So we can just write select star from address, join user using user ID. And there we go. We have all the addresses with their user information attached to them. When you do this, you'll notice that we're getting all of these addresses that have users bound to them, but the users without addresses and the address without a user are left out. That's because we're creating what's called an inner join, and that's the default type of join in MySQL. So when you just write join, that's what you get. You can visualize it like this. You have two tables, and if you found some common results in the overlap, that's what is shown. None of the remaining data in the tables is shown. If we want all of the addresses, no matter if they have a user attached, we can use left join. Select star from address, left join user using user ID. So envision that the tables that we work with are written down on a piece of paper, left to right, as we mentioned them. This one gets you all of the values on the left side, on the address side, and then joins the values on the right side, on the user tables. If we look at our Venn diagram, we still get the overlap, but everything on the left is included. Everything on the right isn't. We can do the opposite as well. Let's say that it's all the values on the right that we want. So that would be all of the users. So then we add the table on the left, the table mentioned first, the address. Select star from address, right join user using user ID. Now, none of these actually allow us to see all of the data. To do that, we'll need to do what's called a full outer join. And that is part of the SQL definition, but unfortunately, it's not something you can do in MySQL, like you can in a lot of other SQL variants. So we'll have to jump through a little bit of a hoop to make a full outer join in MySQL. But since an outer join is a combination of a left join and a right join, we can actually just join our joins. So we can use the keyword union to do that. So we simply take the full query of our left join and then the full query of our right join and then add the keyword union in between. This will get you all of the data in both of the tables, connected where it's bound by foreign keys and otherwise just with null values. Now there is one last type of join that we should address here, the cross join. The point of a cross join is to examine all possible connections. So if we want to know which items any user could possibly buy, we could use this query, select star from user, cross join item. Notice that we're not using any IDs to do this. We simply take two tables and ask for the possible combinations of their data. Now, let's try working with that many-to-many relationship that we built in the shopping cart earlier in the video. If you forgot how confusing it looked, just write select star from shopping cart and rejoice. We can use joins to make sense of this though. We want to see who the actual users are and what the actual items they're purchasing are. So select star from user, join shopping cart using user ID, join item using item ID. And of course, we would generally want to see this for a particular user. Select star from user, join shopping cart using user ID, join item using item ID, where the user ID equals 1. And of course, if we want to know the total price of all the items, we summarize the prices multiplied by the amounts. So we're selecting the sum of the item amount multiplied by the price. When you work with joins, you'll inevitably run into a situation where you need to show a column with a different name than what it has. This often happens when two joined tables have columns with the same name. So let's try adding a description to our users so we can try and handle this. Alter table, user, add column, description, tiny text, default, great person. Now, if we look at all of our users, select star from user, we can see that everyone is listed with the description, great person. And if we make the same join as before, select star from user, join shopping cart using user ID, join item using item ID, where user ID equals 1, then there is a description, but it's empty. And that's because it's the item description, not the user description. So let's give the user description an alias. Select user.description as user description, user.star, item.star. I'm using the keyword as to define my alias. And you can see in the resulting table that my user description now uses my alias. And my item description is just called description. Also notice that I have to define the tables that I want values from in my select query, now that I'm starting to be specific about it. And actually, right now, I'm asking for the user.description column twice because I'm both asking for the user.description and user.star. But this is ignored as long as I'm just dragging data out, but it'll become important in a moment when we discuss views. Let's try setting an alias for a table name when we join them. So here it says, select user.description as user_description, comma, user.star, comma, I.star. Notice that we haven't seen that I before. Join shopping cart using user ID, join item as I using user ID, where user ID equals 1. Here, I'm using an alias to give the item table a shorter name, but notice how I need to use that alias in the first line as well. It's not just something I can do, it's something I have to do. An alias works for the entire query. Even if it isn't set until halfway through the query, I need to use it every time that I mention it, outside of the point, of course, where I create the alias. And since this alias is for a table, there's no visible difference in the output. So now that we have a complex query to find everything in the shopping carts, we might want to look at it frequently and work with it in various ways without having to work with that complex query every single time. And for that, we use a view. So if we say select user.userid, user.email, comma, item.star from user and join shopping cart using user ID, join item using item ID, we get all the items in all the users' shopping carts, but we can save that query as a view in the database by adding the words create view cart as just before the query from before. Now we can treat this more or less like a table. We can say select star from cart where user ID equals 1, and we'll get that information. We can change the user's email address, update cart, set email equal to updated at skillsession.net, where email equals jack at skillsession.net. And you can see that it's updated in the cart view, but it's also updated in the user table. So the data that you insert and update here trickles back to the appropriate tables, but you can only update one base table per query through a view. You can also do joins in it to get all the order information that you need in a glance. So select star from cart, join address using user ID, where user ID equals 1. This will get you every item twice because the user has 2 addresses. But we can simply group by item to say that we only want to see each item once for that user. Now let's talk about data models. When you collaborate on a database, you should draw up a data model so that everyone knows where to find everything, what everything is called, and how everything connects to each other. You would normally use an entity relationship diagram or an ER diagram for short, or a data model for that. You simply outline all of your tables with their names and their columns and draw lines between them to show how the tables are bound together by foreign keys. There are different arrowheads that you can use to denote whether it's a one-to-one, a one-to-many, or a many-to-many relationship. And by drawing these diagrams, you'll increase your efficiency when collaborating and even when you're working alone with a database that just gets a bit bigger in size. Migrations. When you're collaborating on code, you'll normally need to store your code in GitHub or some other Git repository. The same should go for your database. I often see students using the same online database or some other online service that everyone can access while they're developing something, and you shouldn't. Instead, make sure you have an SQL file in your repository which contains all of the code that was used to create your database. Then, when you create some new code that needs the database to be different, those changes become part of the same branch as your code and comes into the main branch with your pull request. You can simply pull the branch, drop the whole database and create it again from your script. Now that's obviously the simple solution. The correct solution would be to use a migration system. I might create a separate video on this, trying it out in different programming languages, but let me just outline the idea real quick. You create a table named migration in your database and a folder in your repository with your SQL files that you also call migrations. Once an SQL file is merged into the main branch, it must never be changed. Whenever you need to change the database, you create a new SQL file in the migrations folder and you name it by starting with a timestamp, year, month, day, hour, minute, and then whatever text you need to describe the content. That way, the SQL files will always be sorted in order. Then you create a script in whatever programming language that you're using, which runs through the files of that directory and checks to see if all file names are present in the migrations table. Select star from migrations where file name equal to 2023 or 101 at 010101 hello world.sql. If it doesn't, then you run the SQL in that file and insert the file name in the migrations table afterwards. That way, the same SQL is never run twice and any developer can always just run the migration script to make sure they have all the migrations that they need on their own computers and thus work with their own local databases. That way, you can also make experimental changes without ruining the database for your collaborators as you go along. If you want to know more about Git and GitHub, I have another video on the channel that goes through just that, and I'll leave a link in the description. So that was quite the mouthful, but I promise you, if you understand the things that we just went through, you'll not have a problem navigating through any databases, not even if they're a different dialect of SQL. So I guess it's time to say, congratulations, you made it through. I have more full courses for upcoming full stack developers coming up on the channel, so make sure to subscribe so you get them as soon as they're ready. And in the meantime, there's a lot of free courses available on my channel already. So take care, and I'll see you in the next one. Bye-bye.